Okay, shall we start? So in the last session, we talk about the bivariate distribution. So in this session, we are going to talk about a bit different, but very related to the last session, which is about the marginal distribution. Okay, so the marginal distribution is that if x and y have the joint, okay, and PDF of x associated with marginal CDF is called the marginal PF or PDF of x. So this one a little bit strange, I know. So let me talk when we see the example more, okay? So two topics. First, we talked about marginal distribution for discrete or continuous distribution. And second, we are using and verifying independence. Okay. So the discrete one, okay, for the discrete one, x and y have the discrete joint and we have PF. So the marginal PF, so let's imagine like this, okay? So that, okay. So let's say we have the distribution like this, okay? Let's say this, the normal distribution, x and this y is a f. Okay, so this one is a joint, okay? For the marginal, let's say marginal as x0, it is as if we take only that piece. We take only that piece of the PDF. And after we get that piece, we flatten out, okay? So we flatten out, let's say, like this. Okay, we flatten out such that this probability is come to 1, okay? Okay. So this one, it is, okay? It is, we take, okay? We take sum, okay? Sum of all this. This is not equal to 1, sorry. It's not equal to 1. So we take this one and we sum the area. It doesn't have to be equal to 1, okay? So we sum the area at this one, okay? So x is equal to x0, sum from y from minus infinity to plus infinity. Thus that it is as if we take the slice, okay? We take the slice out of that one. So that means f1 of x is the sum of all y of x, y. So it is as if we want to get rid of y. We get rid of y. So we have to take into account all possibility of y. So after this one, it will be function of x only. And similarly, okay, and similarly, this f2 of y. So if x and y have continuous joint distribution, okay, marginal PDF of x is integrated, very similar, okay? It is integrated between this one and this one, okay? It is for x0, right? But we can, let's say, take it for another x. Take it for another x, like this. And we take it for another x, okay? Another x is maybe a bit smaller. So the area, okay? Area, let's say this one is equal to 0.4. And the pink one is 0.25. And the brown one is 0.1. Okay. So let's say map from x0 to 0.4, x1 to 0.25, and x2 to 0.1. Okay. So this is as if we integrate from minus infinity to plus infinity. So this kind of function that we take this out of what? We take this all of this one. Okay, so that is we have to integrate and we get rid of y. Okay, very similar. So let's go to the next one. For example, we have the joint like this. So the first thing is that if we want to find the marginal, we have to take the integration. Okay, so f1 of x we have to get rid of y. That is, we have to integrate for all possibilities of y. Okay, for all possibility of y. That is y between x squared and 1. That support may occur here. Okay, support may occur here. So we integrate from x squared to 1 and we get its function. Notice that we start from the PDF, but in the end, we have only as a function of x, not y anymore. Okay. Well, this one is similar. f2 of y. Okay. So this one, x, we know that x between 1 and minus 1, right? And x squared less than or equal to y. We can modify this x less than or equal to square root of y and x greater than square root of y. Okay, so this one is a support. Okay, is a support. So we have to find as a function of y. So if you want to be technically correct, we choose replace this one is a, let's say, it's a minimum. Okay, minimum between what? Between square root of y and 1. But we know that y must be less than or equal to 1 anyway. So this one is equal to square root y. Okay, so we get this as a function of y. Okay, so next, mixed distribution. Okay, mixed distribution. So let's say x is discrete and y is continuous, and we want to find the marginal of x. That is, we have to get rid of y. But since y is continuous, we get rid of it by integration. Okay, integration. But if we want to get rid of x, we have to use the summation. Okay. So the next topic that we are going to discuss is we're going to use independence, which is the concept that we developed in chapter 2 into this kind of setting. Okay. It is said that two random variables x and y are independent if for every two sets A and B of real numbers, we can separate this into this one. Very similar to independence definition that we have found earlier. But this for the version of the random variable, because at the time we didn't define what random variable is yet. Okay, so we could not write something like this, but now we can, because A and B are the sets of the real numbers. Okay, so this one is a simple corollary. Simple corollary because we can define A is minus infinity and x, and we can define B as minus infinity and y. And this one is equal to this one. Okay. Very intuitive since we studied in chapter 2 already. Okay. Suppose that x and y are random variables that have choice P and PDF, then x and y will be independent if and only if f can be represented into this form. Okay. We can separate it. Okay. We can separate it f into h. F into h. Okay. h1 function of x, h2 function of y. Okay, so we need the proof here, but I think the proof you can look at in the textbook. It's not difficult, but I don't see the value of proving this. Okay, so I will leave you the task of doing that. And since we can separate into h1, h2, we can separate it into f1 and f2 because this chunk is a function of x, this chunk is a function of y, and f1 is the function of x, and f2 is the function of y. So this is a simple corollary of the above one. Okay, so first it must be separable, and second, if it is separable, it must be separated into F1 and F2. Okay. So no matter function h and g are, okay, no matter what function are, but this one is the simple corollary of the above one. Okay. So let's look at the second example. Suppose that the random variable x and y are independent with the same distribution. Then determine this probability. So first, since they are independent, so we can multiply, okay? We can multiply these two together. So there will be 4xy, but we must be beware of the support, because similarly, the support is for y is y between 0 and 1. So we must intersect these two conditions together and still otherwise. Okay. And for this one, it is okay. So this one, if we draw the diagram, 1 and 1, right? So if we wanted to integrate y first, okay, so y at each x, at each x, okay, at each x, y must be between 0, okay, 0 and 1 minus x0. That's the education of this part, okay, for the x. And for the y, we can say that it's between 0 and 1. Okay, so we integrate over x and we integrate over y. We have 1 over 6. I think you are familiar with this kind of picture if you study, let's say, the basic calculus. Okay. So next, example 3. Suppose that the joint PDF of x and y have the following form. Prove that x and y are not independent. Okay. So suppose that they are independent. That means they must be factorized into F1 and F2. Okay. So the support defined for the circle. Yeah, for the circle. Okay. So you could see that if x is equal to 0.9, then fx here surely is not equal to 0 for sure, because there's some error here. And similarly, if y equal to 0.9, f2 of 0.9 is not equal to 0 also. Okay. But what? 0.9 and 0.1. If we intersect, okay, I think this picture may not be correct. Let me draw the new one. So 0.9 is here. Okay. And for the red one and for the one is here. Okay. But if both are 0.9, they are here. So this probability is 0 because it is not in the support. Okay. Not in the support. So it's equal to 0, but this one not equal to 0. So we cannot factorize that. Okay. And for the special case, for the rectangular support, x and y have linear distribution. Suppose that this support is a rectangular region, okay, and parallel to the coordinate. X and y are independent if and only if fxy is equal to hx and h2y holds true for all xy in R. So for xy in the support in one we hold true. For the outside, it doesn't matter. Okay. So in the last example, since the support is a circle, we cannot use this property. Okay. So that's the end of this lesson. Okay. And there are more topics to discover in the next lesson. So see ya. Okay.